Yeah, so now I'm recording it. Yeah, so one exam question is still missing. So I have done all the others, like on histories, on recovery. What else was missing? So of course there's an exam question on window functions. There's also one exam question on quorum consensus, as we discussed. There's one, of course, on SQL and how to use decorrelation, and yeah, and I'm still missing one question. So I still don't know. So I'm still looking for inspiration. So one idea would be about xquery and JSON path. So let's see whether this will be the exercise for next week. Yeah, so what I wanted to say, that there is an XML file integration. This is standardized in SQL. Whereas for JSON, there are a lot of JSON integration, but there's no standardized query language for JSON. So for XML it's standardized, but for JSON it is not. But there are some there are query capabilities in PostgreSQL, and I think I will show them next week or this week. Okay, so XML files itself, it's better standardized than CSV. It's semi-structured, as you see, because like it's not always the same structure. So in contrast to relational database system, all the data has to fit to the same structure. So it's the same like CSV. In the first line, like you have the header, and the header decides on the structure. So CSV files are structured, and in contrast, XML files are semi-structured. So it does not, the data does not necessarily has to follow the same schema, but there is kind of structuring by opening and closing tags. So this is the big difference. So you can also specify about the opening and the closing tags, and this is called XML schema here. XML schema, it's written as XML and describes what is allowed and what is not. So this would be XML schema, but I won't discuss this here in the lecture. I have some slides if you're interested, but I don't want to discuss this in more detail. Only how to query XML. Of course, the next, so actually the same idea like XML, but it's better readable, is JSON. So it comes from JavaScript object notation, and I think in research this is the most commonly used kind of semi-structured data. So it's also semi-structured, and you have arrays. Arrays have a certain position, so arrays start with this kind of brackets, and then curly brackets are used for sets. So here like you have the first entry, and then you have the second entry, and inside this is a set, and you always have first the attribute. So this is the content, the value, and this is actually the attribute name. So this is actually how JSON looks like, and it's much simpler. Okay, so these are the different kind of text-based formats. And so the idea is, okay, how can we process it before we load the data into the database system? And the idea is, okay, you have all the command line tools that are available on Unix or Linux. And actually it's much fun to use them. So when I was on an exchange semester in Paris, I only had one lecture on using command line tools and how to create makefiles. And command line tools are perfect to get a first impression. And so whether it's worth the time creating a script, here's the XKCD comics. So it's about, okay, how often you do the task and how much time you shave off. So this is how much time it would need to create the script. So if it's only 5 seconds to create the script, and if you use it, what is it, yearly, monthly, or 5 times a day, or 15 times a day, and basically here you see it. So if you use it a lot, but it would take more than a day, it's not necessary. Or is it correctly? Across 5 years. How often you do the task, yearly, and how much. So this is actually how much work, how much time you should put into developing a script for doing some automated tasks. So that's the idea of the XKCD comic. So, okay, so this is how much time you save, and this is how often you do the task. Yeah, so it's just as a teaser why you should do some scripts, and basically it's only efficient if you're spending more time than you save. Yeah. Okay. So some basics on Linux command lines. So the pipe can be used to concatenate commands. You can redirect to a file, this equator or less symbol, and you can read from a file with the other side. And like in Linux, you have two streams. Like you have the normal standard out and you have the standard error. And you can redirect the standard out and the standard error stream. So with 2, this is the error stream. And instead, with 1, this would be the standard out. So 1 would be standard out, and 2 would be standard error. So, to just show you how this works, so for example, these are all the lecture slides, and I wanted to grab, for example, for a certain command. So I wanted to say, okay, so with cat, this is the most basic one. And with cat, and for example, if you want to output all the content, you can use cat. So cat just concatenates multiple commands. So this is to open any file. You can also then, instead, you can look for a certain word, and looking for a certain word would be using grep. So for example, we can, if we want to grep for this slide, we can just enter the header. So it would be combining tools, and then you would see, okay, you see actually how this is written. So all the tools normally, they can, as a second argument, they expect the file. So if we have here the file, we can, but we cannot see the line, okay. Yeah, so we can either, so if we want to have it as input, we can use it as the second command, or we can also use it as the first one, and then here you see the pipe, which redirects it to the next command. So here with the pipe, we can concatenate every kind of, sorry, where's my mouse? So here you see with the pipe, we can redirect, we can concatenate multiple commands. So this is the pipe, can be used for everything. Okay, so anything else I want to show? So if you just want to have the head of something, so only the first lines, you can say head, and then this shows you only the first, how many lines do we have? 1, 2, 3, should be the first 10 lines. But you can also be more precise. You can say, okay, I want to see only the first 5 lines. And here you can also increase the number, for example, head. And then, as I said, you can concatenate it to anything. So here we can again grep inside, and we can grep for CSV, for example. And then we have, from the first 50 lines, all the lines containing CSV. So this is based. And then, if you want to save this, you can redirect it here and say, okay, it should be stored inside of a text file. So then the output we have seen is now in this text file. Okay, so these are actually the basics about using command line tools. Other things, for example, instead the opposite of head would be tail. This shows you the last, normally 10 entries, or in this case the last 50 entries, or only the last one. And in contrast to cat, so cat outputs you everything, and there are also some which allows you to scroll. For example, less and more. Less shows you all the files, but if you quit, you return to the original command line prompt, and the same does more. But in contrast, if you end, you see all the things printed onto the command line prompt. So this is actually the difference between more and less. both both commands show you everything inside of a file. Also cat, but cat directly prints it onto your screen. Yeah. So we have seen where's my mouse here? So I've shown you grep. So normally grep expects a second argument, the original file. So you can also just read it from a file, and this in this case would actually do the same. So now you have seen both kind of commands redirecting to a file, just writes it down into this file, and redirecting from a file. So sometimes the argument supports a second argument where it reads, otherwise you can redirect it from a file like that. You can also put some whole commands inside. So instead of just redirecting, you can say, okay, we can pre-process it somehow, cat basics, then we could give us only the head. Okay, and this would also work, but then, okay, why cat basics head n, okay, how many lines we should have? Okay, so this would also work. So you can also enter whole commands inside of this symbol. Yeah, so basically that's how you use bash and how you can pre-process some data for getting a first impression on text-based data. Okay, so now you have actually seen almost everything. Yeah, I have another idea. So the last one, the error stream. So fun fact is you have everything is printed onto the prompt. But actually there are two kinds, the standard out and the standard error. So everything what is intended is standard out. So this what you see is all standard out. But actually as soon as we do a mistake, for example like that, this is not what you see here. This is not standard out, this is standard error. And if you want to avoid error messages, you can just ignore them. For example, by printing them to def null. So def null is just, if you want to ignore something and try to avoid it, it's just device, and null is just to throw it away. Okay, why doesn't it work? I think it's with ampersand, isn't it? Oh no. Actually it should. Oh, it didn't work, sorry. Okay. So this is not the warning message on standard error. So what kind of standard error would exist? So next time, so with your program in C++, and all the warnings will be printed on as standard error, so then it's more useful. Yeah, and yeah, with 1 is standard out, and 2 is standard error. Yeah, so now we would have printed the output to def null, and we can also output it to asdf.text, and then if we enter asdf.text, we should see the whole output. So if we now, yeah, and here you see it what we have printed. Okay, so these are the basics about combining tools, command line tools. And yeah, so as I told you, cat actually means concatenate, and with concatenate you can read a single file, and also, of course, as it is concatenate, you can concatenate multiple files. So cat, for example, accepts piped input. So this is the pipe, so any command you write, and then you can just use cat. But most of the time it's not necessary, because all the commands printed through the output, but only if you want to concatenate more than one. So if you have a second file here, So if you, for example, say, okay, you want to print file 1, then you want to print the output of the first one. And by the way, if you want to output what you get from the pipe, you can just use a minus. So minus means, okay, let's use what's coming from the first command, and then you can print, for example, the second command. So I can show you. So if we would have, for example, another grep, and then you could say, sorry. Then we could say, okay, cat, then it prints, of course, and then if we use the minus, it also prints it, and here we can add something else, for example, basics. So for example, we can also cat asdf.text, and then first outputs the content of asdf.text, and then what's coming from the pipe. So first things I'm putting at the end, and this is printed first, and then what's coming from the minus. Okay, so cat accepts piped input, and okay, if you want to escape binary data, you can use -v, and there's also a cat for every kind of compressed data. For example, if you're using how's it called, X compressed data, so with tar, TIR, you can compress and zip data, but in other kind of formats. And for example, you can use XZ compression or BZ compression. And then you do not need to uncompress them, you can use them as input directly. Okay, so as I've shown you, to inspect whole files, and you want to paginate them, you can use less. And of course, the most useful command is grep. Here you can enter any regular expression. For example, this would give you all the images with multiple numbers. So 0 to 9, and this multiple times, so 0 times, 1 times, or multiple times, and they should end by JPEG. So this would all give you the input of file 1 and file 2, and give you everything, all the images that are referred to in these files. Okay, so grep also accepts it as a second argument, the input files, and star is a regular expression for replacing all the files. So star means everything which is located in this directory ending by HTML. And yeah, there are also some other kinds of returning only the match. Just shows you, okay, so there are different options, and with man, so if you have man page, man grep, so here you can see all the options, for example, for grep. And then if you need anything, you can use manual, and here you can just count the number of occurrences instead of returning them. And here -O means print only the matched parts of a matching line, with each such part on a separate output line. Okay, we can try it out. And then -O. Okay, just instead of printing the whole line, just prints you the output. Okay. So with this symbol, you do the opposite, only return non-matching lines, and also you can disable sensitive search with -E. Yeah, so grep is one of the most useful tools. I'm also using another tool, it's called Silver Searcher. Actually it does the same as grep, but sometimes faster. And you can use it just using AG, and it's called Silver Searcher. Yeah. So here are some examples. So I'm not sure which kind of file he was using. So if we I have it somewhere here. So these are some examples how to first uncompress and concatenate a XZ file, and then you can grep, for example, and here you can also concatenate. So first you can use from, and then you look for a certain domain, and finally here's something to extract only the email part. Okay, so some more kind of commands you might use. So sorting, you have like a sort operator inside, and sorts just sorts you all the characters, all the string as a string. And you can also enable numerical sorting. So normally if you would have a sort, it would sort by 1, 10, 11, and so on, and then 2. So this is the normal problem with alphabetically sorting. So normally if you would have sort, you would have 1, 10, 11, and then would come the 2, 3, and so on. And to avoid that, you can enable numerical sorting with -n. If you have a comma-separated file, or normally it's like a tab-separated file, you can also say, okay, you have to sort by the second key. So for example, if you have like anything as first one, but want to use it as the second attribute, you can say, okay, the key is the second one. And I think you can also add the delimiter, but I'm not sure about the command. So, as I said, if you don't know about the options, you have to look into the manual. So you say man sort, and then here you can see how you specify the delimiter. So here's the key, and where's the delimiter? Here with -t. So with -t, you can specify the field separator. So if you have, for example, a file like asdf.csv, and we want to, this should be comma separated, and you want, for example, to sort by the second column. So normally if you would enter sort, it would just sort you by alphabetically by the first one, but then you can enter the key. So you say the field separator should be the comma, and then it should be sorted by the second, and then it would be sorted by the second column. So you see, you can use it like a database and sort it. Here sorting with explicit separator and the third key, and you also can eliminate duplicates with -u. So you have a powerful sorting algorithm inside of the bash. Okay, so as I said, with head and tail you get either the first or the last entries. You can also do the opposite, everything but the first two entries. So you can skip the first two entries with tail, but say, okay, you should start at the third line, and you could do it also from the other side. Everything but the last two entries. So you can use sort and then using head and tail for min-max computation. Okay, so as I said, with sort you can eliminate duplicates, but there's also a certain command for it with unique. You can also eliminate duplicates, you can also count the number of duplicates, or return only the duplicates, or return only the unique lines. So you can also create a group operator, so an aggregation inside of the bash. So here we are again some examples. So where is it? Yeah, here. So you can sort, how to use the sort operator, how you can count the duplicates, and then only those without duplicates. Okay, so like the projection in SQL, this would be the cut operator. So cat does the same as cut, but only returns certain columns. So it's like the projection in SQL. So like the select clause in SQL this would be the cut command. And here you can say, okay, you want only the first and the third column. And so normally, as I said, it would be white space separated, so it would only consider tabs. I'm not sure whether tabs and spaces, I think spaces are also included. It's just separated by white space. And you can also specify a delimiter. So this is kind of strange that every command has a different option for the delimiter. So you remember in sort it was -t, but in cut it's -d. So this is kind of strange that every command has a different option parameter for the delimiter. So in cut it's -d. And here you can say, okay, we only want to print the second and the fourth column. Okay, and here, if you do not interested in the fields and the columns, but only want to consider the characters, you can also say, okay, we want to only print the first until the 10th character. So this is cut. In contrast to cat, only prints certain attributes. Okay, so more easy for an aggregation, it's for example WC, it's word count, and word count gives you the full statistics on the number of lines, the number of characters, and the number of words. If you only want one of these statistics, for example, you can just count the number of lines, or can also just count the number of bytes. So this is quite useful if you just want to know the number of characters inside of a file. So if you have a character limit, you can just use word count to know about the number of characters used in your text. Okay, so you can also shuffle the lines of the input. So random order gives you with shuff, and then you can also get some random sampling. If you just want to have like the 10,000 samples, you can combine them. Yeah, but I never used this shuffling command. So maybe again, let's have a look how this was used. So here, count the number of a mail in the archive. So they have kind of a Linux kernel email archive. And first we grab by the subject, and then we want 20 random samples with grab and shuffling. And then we want to have the most popular one, and therefore we have to apply unique and count the most common ones. Yeah, sorry for not having prepared this kind of file. Okay. Another very useful command is SED. So actually SED is Turing complete. So you can do everything with SED what you want. But normally, so the common use case is replacing text. And if you want to replace all occurrences within a text, you can just say, okay, substitute S, then you can enter the old text and the new text. So when I was attending the course on Bash command line tools, I did everything with SED. So I avoided all the other tools. I didn't do anything with cut. I did everything with SED. So with SED you can do anything. You can select multiple lines. You can select certain attributes. You can do everything. Really everything. It's Turing complete. But normally you shouldn't use it for everything. You only should use it for replacing text. And yeah, so what's the first difference between the first and the other side? Okay, yeah, so normally it replaces the first occurrence of a text by the second, but if you want to replace all occurrences, you have to enter a G at the end. Okay, so what else? So what's really useful, the command -e. With -e, it's in place. So normally it would be printed to the normal standard out, but with -e, you change the original file. So -e changes the original file, so then you should have made a backup before. So with -e, always ensure that you have a backup. Okay, so what do we have here? So we also allow regular expressions inside. So this is a regular expression here. So at least, so 0 to infinite number of numbers. And what actually now the important part are the brackets. So here you can see the brackets that were used, the first one and the second one. So here the brackets, and basically now the trick is you can refer to what is inside here. So of \1 you basically print anything which was occurring here. And this is the back reference. So for example here, if you want to rename all the images which were named IMG and you want to replace IMG just by image, you can keep the original numbering but just change the prefix. So this is called back references. Yeah. So normally it would be case sensitive, so upper and lower letters would would make a difference. But if you want to turn it off, so if you want to have case insensitive matching, you can use a -I, big I at the end. So then all the files with either upper or lower letters would be replaced. You can also use multiple patterns. The first one, substitute first the first one and then substitute the second one, and here. So as I said, SED is theory complete. You can do anything with SED. Next, you also have sort merge joins. And so like you have a join operator, and as I said, join expects sorted input files, as you can see here. And normally it would just join by the first column in each file. So it would always just compare whether the first column is the same and would normally only output matching files. So it would just do a natural join normally on the first one, but you can also specify the join parameter. So if it should be the join, the key would be contained in the second column. Here you can say it should be the second column, and for the second file it should be, for example, the first column. So as I said, normally it expects white space delimited files, but if you have other kind of delimiter, you can specify it here with -d. So then it uses comma separated values in file 1 and file 2. And you can also do an outer join. For example, here you would do a left outer join if you say, okay, you would preserve all the unmatching lines also from file 1. So basically you can do all the join modes which exist. So left outer join, right outer join, full outer join, and just a normal natural join. And I think you can also have an anti-join and kind of other joins. So if you have a manual join, you see all the different options. Of course, you can also support header. No, so anti-join is not possible. Okay. Yeah. Okay, and as I said, it only supports sorted input. So it's actually a sort merged join. So if the file 1 or file 2 is not sorted, you have to run sort beforehand. Okay, so there are two Turing-complete command line tools. The first one is SED and the second one is AWK. And the AWK just allows you to do any procedural code, any procedural instructions. So you have, for example, some initialization and some post work, and inside this would be performed in each line. So for example, if you want to count the number of lines, you would start by 0, and for each line we would say, okay, increment this variable by 1, and at the end you should print the output. If you want to sum up a certain column, you can access this column with the $ symbol, and yeah, you can also then create some average, so we have to sum it up and count it, and also its conditions inside are supported. So AWK is the other Turing-complete tool on the bash by default. Okay, here are again some examples how you can use AWK. Sorry. Yeah, so here find the most popular words in the LKML dataset. So we first replace, okay, so the first thing is we replace every word by a new line, and then we sort it, and here compute the average number of lines in our email, and therefore for each line we count how long it is. Yeah. Okay, so much about command line tools. So basically these command line tools will help you for everything when you use a Linux command line. So whenever you log onto a computer, on a server, these are the commands you should use. And yeah, so now the idea is, okay, why is it important to use a database system and not to do everything with command line tools? So and here the idea is, okay, what is the performance spread of high-level tools to handwritten tools? What are the limits? What is the impact of careful programming? And so there's a toy problem. So the idea is, okay, we have the TPCH dataset, we have the biggest relation, the line item relation, and want to sum up the quantity, which is the fifth column. So 1, 2, 3, 4, 5. So the scale factor, as I said, for TPCH is, as I said, is the data set for benchmarking relational database systems. And you can specify how big it should be. And this is called the scale factor, and scale factor 1 corresponds to 1 gigabyte. And yeah, so let's assume we have, for scale factor 1, the line item table itself is 725 megabyte big, and it has 6 million of lines. And now how would it be processed if we only have text input? And yeah, so what are the limits if we just process it as a text input, so not as a binary format, but just using normal text input? And then the idea would be, okay, if we have 1 gigabyte Ethernet, if we have a bandwidth of 125 megabyte per second, then it would take 6 seconds just to consume it, so just to compute it on with normal tools. And then if we would store it on our HDD, it would take 3.6 seconds, and if it would be fully located in RAM, it would only take 0.04 seconds. Yeah. So this would be the optimal code if we just have our C++ file reading the data. So this is the perfect one. So this is text-based. It's text-based input, but with a C++ program, with a written C++ program executed. So this would be the performance limits in the best case. Okay, so what was the task again? Summing up the fifth line, and so using AWK, this would be the corresponding command. And if you execute it, it would take up to 5 seconds. And we can see that the first one is if we load it from disk, and the second execution would be CPU bound, as we have cached it. Really? So comparing it to a similar implementation in Python, we can write a small Python program to compute the sum. So this would be the same code in Python. It's again CPU bound, and then this would be the same program in C++, and this would be I/O bound. So the first one would be I/O bound, and the second one would be, when it was cached, it would be CPU bound. Okay, so you saw the same implementation. It's the same program in 3 different implementations. And now the question is how you can you measure performance. And the idea is, for example, if you want to measure performance, you should always use perf. So perf so you have to enable it in your machine to get all the statistics, and with perf you get all the information about cache misses and instruction per cycles and so on. And yeah, so here you can see how you can optimize the code. So with mmap, you can mapping the file directly into memory. So then you would map the buffer page from this into main memory, and this would increase the performance, as initially the cache was cold, but in the second one you could use a warm cache, so with already loaded data. And yeah, there are other kinds how to speed it up, but actually I do not. Actually, my idea was to just show you the different kind of file formats and how you can use all the files, and then we can do a similar, how we can integrate the files in SQL. Okay, here's another implementation using threads, and finally here we can see the different performances with AWK, and finally with C++, and how we can optimize it with C++. So basically what you see, implementation matters, and you have to optimize it until it's not IO bound anymore. Yeah, so I just remembered that actually I forgot to tell you about in-memory database systems, about code generation. So last week we did not finish, right? So I have to continue that. Okay, and here are some slides when we should use a cluster. So then you would always have to consider network bandwidth, and yeah. Okay, so much about command line tools. So you see quality of implementation matters a lot. For the first impression you can use command line tools, but then if you want to be faster you have to use other kind of programs, and then you can see like network speed is a problem, so that you can parallelize, but then using remote CPUs is difficult, and we often prefer scale up, so use at the same machine, then using scale out, transferring the data to another machine. Yeah, so let's continue with the slide I forgot last week, because I want to still continue with relational database systems actually, and I forgot the last chapter. So we ended up with parallel query execution, and I wanted to show you about code generation. Yeah, so we have to discuss this again. So sorry. Okay, so you remember the different kind of execution styles. So like we have our operator plan. For example, we have a join, and we have, for example, a table scan, R and S, and then we have, for example, a projection and a selection, and so on. And like you remember, normally it was with next. So all the operator asks for the next tuple, and next tuple, and so on. So this was the normal volcano-based execution model. And now the idea was, okay, it was replaced by consume and produce. So instead of having to ask for every tuple, for every operator, next, or I don't want red, I want green, next, we ask first produce once, but only once, and afterwards we say, okay, consume all the tuples. We have a second arrow just for consume the tuples. So we have to produce and consume. You remember that, right? So, okay, and we have now another kind of optimization. So instead of saying produce, consume, the idea is, okay, we have like two phases. We have the first phase, so the first phase, which would be just the compilation. And then the idea is, okay, we only call produce and consume once. Instead of returning tuples, we are just emitting the corresponding code parts. And then we would have a second phase. And the second phase would be the runtime. And then we are running the code generated by produce, consume. So this would be the idea, that this produce and consume would be only called during the first phase, the compilation phase. So the idea is that at runtime, we avoid any produce, consume calls. So instead of returning tuples, we now return code. And this is the big idea. So code generation means instead, like the original volcano style interface, where we return tuple and did it all at runtime, code generation means we call produce and consume only at compile time, but then at runtime and produce, consume only return code. So that's actually everything. And these are the slides I forgot last time. It's only about two phases. One phase is compilation, and second phase is runtime. And like at compilation time, you call produce and consume only at compilation time, and then you only return the code, which is executed afterwards. So that's it. And all the slides I forgot today, actually I couldn't explain last week, were about code generation. And the idea is, okay, for all the operator subscripts, so which access of a certain line, they will be compiled into either bytecode or a kind of virtual bytecode, which will be translated afterwards. So the idea is basically we have LLVM. So this one, no. So LLVM is low-level virtual machine assembler. And the idea is, okay, normally you have like the code in a custom programming language, and then you have a target machine, and this would be, for example, x86 assembler, or it would be AMD 64 assembler for 64-bit architectures. Michael Engel, for example, would like to have database systems on RISC-V. It's an open instruction set. Or another kind would be, for example, on your mobile phones. These are all ARM-based. So normally it would matter the target you have. You would compile it for every architecture once, normally. So this would be a normal process. So if you have, for example, a code written in C++, you would call CC or GCC or G++ to compile it. Now the idea is, instead of compile it directly for each target architecture, the idea is, okay, instead let's introduce an intermediate step, and this would be, for example, LVM. So let's have, I'm drawing, so this would be LLM. So LLVM. And this would be low-level virtual machine assembler. And this would be, then it's called intermediate representation, because like it's kind of virtual bytecode. So it would have one register for every instruction, so it would start with 1, and this is the first, and this would be, for example, a comparison of different other operators, and so on, and so on. And finally, if you then run it on a target machine, this would be translated directly into, for example, AMD 64 assembler. Yeah, and that's the idea of code generation. It's that you compile it to a target architecture. This might be directly, for example, with from C++ code to AMD 64. For example, currently I'm doing GPU database systems. The idea is, okay, then instead of having ARM, you would have, for example, NV NVIDIA GPUs, and this they would expect PTX code. PTX would be the format. And so this is what I currently do, but I avoid LLVM-IR. I would compile it directly with NVCC and would have then the CUDA files. So it's similar to C. So this was what I'm doing right now. Generating CUDA files, which is kind of C code from the operator plan, to be run on the GPU. Okay, so that's the idea. So remember, produce, consume, emitting code, and this code must be compiled, and there's some kind of intermediate representations in between. Okay. So single instructions, SSA just means single instructions, but for what the second S stands, I don't know right now. So the idea is, okay, for every line you have a single instruction, single line, and basically this will be translated afterwards into the AMD64. So these are the tags. So to remember some breakpoints or some jumps where you have to return. So these are the labels. Yeah, and this is actually the LLVM code, which would be the output when generating the code to LLVM. So I never used LLVM directly, I was just using frameworks generating LLVM. Okay, so sometimes you can also call from LLVM directly C++ code. So you have to define an interface in between. This is kind of complex then, so it allows LLVM to call runtime functions from C++, and yeah, but the real challenge is integrating these into set-oriented processing. And yeah, so the second piece now you learned was, okay, we have produce, consume. Produce, consume basically inverses the tuple flow. The second thing now you have learned is we generate the code, and the next question is, why are we doing this? And the call is data-centric. And basically what the idea is, we want to keep the data, like the data items in main memory. So the idea is, normally you would get all the tuples. With next you would get a whole tuple, and you would have, okay, you would fetch the tuple and you would hand the tuple over to the next operator. So you would move the tuples. And so now the idea is, actually what we want to have a big for loop. So the idea is, at the end, we want to have a big for loop, and the idea is we would to process everything like it is in a big for loop. So A would be a struct somehow, and then we would say, okay, let's compare if A dot value would be greater than X, then we would do anything else with it. And the idea is, okay, we want to do it once for each tuple, and this is called data-centric. So the idea is, okay, iterator model is the normal operator model, so iterator model is the volcano model with the next. And now the idea is, but then we would hand over each tuple single. We would hand over each tuple, and now the idea is, instead of handing the tuples, we want to have a data-centric execution, and the data-centric execution means actually we are keeping the data in register, and we just perform all the operations. For example, if we now want to do an add, we could say, okay, a.b should be added a certain value, or kind of another value should be added, and so on. And this is the idea. The data can be kept in registers while we perform certain operations on it. Okay, so the data should be kept in CPU registers as much as possible, and what actually differs is are the operations and not the tuples. So that's the idea. Increase locality, reduce branching. So here again, what you should always know is about the pipelines. So as I said, what kind of operations do we have? Here we have one join, and we have a selection. So if we want to reconstruct the original query, it would be, so we would have two tables. We would have R1, R2, R3, and we would have, of course, the join conditions, and we would have we would have an aggregation before R2. So we would reconstruct the original query. Sorry. Can't find my mouse. So here it is. So how would it like? So we had the first one, the select from R2, where y is equal to 3, and we would group by z and would count everything. So then we would have the join select star from this query, and the second one would be R3, and the where condition would be where R2.z should be equal to R3.c. And then we have another pipeline, select star from R1, and finally where x should be equal to 7. Okay, so this would be actually the query, which would be here. And you see we have 3 pipelines. This is the first pipeline. Then we have here another pipeline. So as this is an aggregation, this breaks the pipeline. So here starts another one. This is the left side of the join operator. So here we have to materialize it. It would be normally a hash join. And finally, we have a third pipeline at the end. So it would be somehow, this would be the first, second, third, fourth. Okay, so this would be the pipelines which would be created. And yeah, data is always taken out of a pipeline breaker and materialized into the next. So this is a pipeline breaker, this is a pipeline breaker, and operators in between are passed through. So for example, the selection is just passed through, and the relevant chunks are the pipeline fragments. Instead of iterating, we can push up the pipeline. So the idea is, okay, all the code which belongs to a pipeline. Oh, you can't see my mouse, sorry. All the code which belongs to a pipeline basically is inside of a big for loop. So this is inside of a big for loop, and this is inside of a big for loop until it gets materialized. And the idea is, okay, so we can process each tuple, keep it in registers until the pipeline ends. And that's actually the idea. Keep it as long as possible inside of the registers. So this is actually the big plan. So yeah, I said it's all inside of a for loop. So here you can see the big for loops. So we have at first this for loop materializing all the results of R1. Then we have a second for loop from computing the aggregation here. Then we have a third for loop for building the hash table for this join, for this hash join. And finally, we can have a big for loop for all the tuples in R3, where we can perform all the joins to output the results. So this would be the idea of code generation, to produce consume. And then the idea is, okay, we have each operator has a certain parts. So for example, the selections here is just translated into an if statement. So these are all the selection operators. Every table scan is actually translated into a big for loop. this is actually a big for loop, every table scan. And also the join operator is also implemented here. This is actually the result of each join operator. And like a join operator always has two sides, building the hash table and probing the hash table. So this does the probe and the other side does the build. Yeah. And also, of course, we have one pipeline breaker. This is the aggregation. And this, oh sorry, I want to use another color. This is the aggregation and this is done here. Yeah, so this is the idea. And produce consumes just outputs you this code. So it's indeed, you have like produce, and produce just says, okay, emit this kind of code. This is really what produce and consume normally in a code generating database systems are doing. They are just emitting these code snippets. Is anyone coming to choose a chair tomorrow? Tomorrow it's choose a chair. You can pick and choose a chair. And I've created a new poster where I explain produce consume on the poster. And I have written some code. But this is my poster for tomorrow. So if anyone visits me, you will see this kind of poster. And here actually you see producing code for NVIDIA GPUs. And the idea is, okay, you only have two operators like produce and consume, and they are just used to create code. And for example, for the table scan, this would be the code generated for the table scan. For example, here in GPUs it would be just the index instead of a for loop. So on CPUs it would be a big for loop. But on GPUs, as you have a different kind of execution style with this single instruction, multiple threads, you would just say, okay, this is the thread you're working on, this is the tuple, which would be used as an identifier, and then here you can see the corresponding code. For example, this is the selection, and the selection here is just translated into a single if statement. Yeah, we have cheated in this implementation as we have used an index join, so we could just use, because it was sorted, for example, the table products was sorted by the index, we can just use the foreign key, which is here given as the product ID, to identify the tuple. So this would be an index join. Here the same, this would be also an index join. And this would be the hash table we are using. So this would be the key and the value. We are finding the slot by the hash value we are doing, and like we have some atomic operations to do not throw away any values, and that's it. And this would be creating the query plan and doing at the end the aggregation. So this would be how we can do produce consume, how you see it in action. Yeah. So basically produce consume implemented for GPUs. This is also what I'm currently doing. Okay, so here's the same but with pseudocode. Okay, so basic strategy, how to do it. The producing operator loops over all materialized tuples. This is the big for loop at the beginning. The current tuple is loaded into CPU registers. And then the pipelining and register operators are applied, so every selection and all the map operators and everything which can be part of a pipeline can be applied. And finally, the tuple is materialized for the next pipeline breaker, for example, the join or the aggregation. And the idea is, again, to maximize code and data locality. And like we have the loops to perform the number of operations, and memory access is minimized as we keep the memory at the data always in registers. This is called data-centric query execution. Okay, and now you will see some examples of how to produce the code. So like you have seen it for GPUs, and now you see some pseudocode for the most common operators. And like the idea is, okay, produce logic generates the code to produce output tuples, so, and consume logic generates the code to accept incoming tuples. And yeah, so basically what I will ask you in the exam will be, I will show you some generated code, and you have reconstruct the original query. So this would be like how I will check whether you understood code generation in the exam. So you should be able to read code snippets and think what will be the original query. Okay, so here you have produce for the hash join, and here like produce would say, okay, produce left side, and the left side would say, okay, you have to consume it, and then you would have to create the hash table for probing it, and then produce right would say then, okay, produce right would then give you the tuples for probing. So here, so if you have to consume, you have to check whether it comes from the left side or the right side. For the left side, you have to build the hash table. Here, this is actually what you need for creating a hash table with LLVM. And for the right side, you have to probe and look up whether the value is inside of the hash table or not. Yeah, and actually, yeah, and then at the end, you have to propagate it to the parent tuple.
So there's also sandblasting.
So basically, I give you, it would be not on with LLVM, it would be like, I give you C++ code, and from the C++ code, you should reconstruct an SQL query. Actually, it's fun. Okay. So far for today. Questions? So I want you to have understood how code generation, the idea, how it works, that at the end you have like a big for loop like this, and from this for loop I want you to understand what kind of SQL query was used. So this would be of importance, yes. Okay, if there are no more questions.
This is the chapter with the running string, right?
Mm-hmm.
Can you open the chapter for
This one?
Next?
This one?
One.
Yeah.
Can you explain the arrows on this? Because I don't quite understand. I think I understand the relics or the adaptive one, but I don't understand like the arrows.
Which arrow? With the points or with
between the nodes?
So with the dark lines, so the non-dashed ones, right?
Yeah.
So basically it's like, the idea is, okay, it's everything is kept inside of main memory. So the idea would be, actually this would be an address somehow. So like this would, actually these are just C++ pointers. Like if this would be in main memory, like this would be somehow memory location like 1, 2, 3, 4, for example, and this would be located at another memory location, for example A000, and so on. And this would be another memory location. What might it be? B1, 2, 3, and this might be another memory location, so 2, 2, 2, 2, and so on. And actually inside of so this is actually where the node starts. So the first value would be located here. And now the idea is, okay, what's inside of the second part? Basically, these are just pointers. So this depends highly on the system architecture. So inside would be, for example, just a pointer to this node, and this node would have a memory address. And the idea would be, okay, 0xA 000, for example. And this would be another memory address, for example, what might it be? F1, 2, 3, and so on. So actually inside there are just memory locations. And these are just pointers to another memory location. And so on. So here inside it would be this memory address, 0xb123, and this would point to the beginning of this node.
Okay, so like the direction of the arrow is just a general direction, not like the
Yeah.
pointer.
Yes,
Like,
yes.
okay, I was just
So actually, to be more precisely, it would point to the beginning of the node.
okay. But so the basic concept is just simply like key 0, for example, would have a pointer 0 that would then point to whatever it says in the.
Yes, yes. You're totally right. You're welcome. Any other questions? If not, let's continue in 5:45. And if you then have another question, we can discuss it here. So let's make a break. 50 minutes.